Jain to all. Today I am here to present the fifth video lecture of the subject Control System BEC 602. I am Dr. Amit Garg, Associate Professor in ECE Department of AKGEC, and the topic of the today's video lecture is basically the block diagram reduction. So block diagram reduction is basically a technique by which we can find out the overall transfer function of a complicated system. You see, whenever there is a plant or whenever there is a system which is a bit complicated, then that system is basically represented by the combination of various subsystems, and it is also possible that those subsystems are also composed by various subsystems. Okay, so this is how a complicated system will work. Okay, so now here sometimes it is important to note that it is important to find that what is the overall transfer function of the given system. Okay, so there this block diagram reduction technique is very useful technique. Okay, so let us see. So block diagram reduction in any complex real-time system, many individual subsystems exist, that I have already told to you. These subsystems can be represented by means of individual blocks. If you will see, each and every subsystem is represented by blocks, and each and every block is having some transfer function. Okay, so the individual blocks of each subsystem are combined to form the block diagram for the system. So block diagram means when each and every subsystem will be represented by a block, and when we will combine all those subsystems, or you can say when we'll combine all those blocks, so whatever we have is basically the block diagram. Okay, so by seeing the block diagram, you can easily identify that what are basically the components involved in that. Okay, these individual blocks contain the transfer function of each subsystem. Block diagram reduction is a technique used to simplify complex block diagram in control systems, making them easier to analyze and understand. Okay, so once we can reduce the block diagrams, so we can easily find out the overall transfer function, or you can say in simple so once we will find out the overall transfer function, then it is simple to analyze that system. Okay, that is the benefit of using this block diagram reduction technique. It involves using rules and techniques to combine blocks, rearrange elements, and eliminate feedback loops to find the overall transfer function of the system. So this is how this we will see all these things, that how we will combine the blocks and how we'll eliminate the feedback loops to find the overall transfer function. So these are the elements of block diagram representation. Okay, so one is summing point, another one is takeoff point. So these two are important elements that will be present in almost in each and every you can say block diagram. In each and every block diagram, you are having summing points and takeoff points. Okay, so this is basically your summing point, where so a block or an element at which two or more signals are either added or subtracted is known as the summing point. Okay, the diagram denoting the summing point for the block diagram given as in dotted lines. Okay, so you can see this is basically the summing point. Here you can see there are two types of signals which are adding, one which is one coming from input and one coming from here. Okay, and another point is basically the takeoff point. The point at which, this is the takeoff point here, the point at which a signal is applied to two or more blocks. So you can see here, from here you can see one signal is coming from here. So one is going to this direction and one is going to in this direction. Okay, so the point at which a signal is applied to two or more blocks. So you can see basically it is applied to one or two blocks, two or more blocks is known as takeoff point. This signal might either be an input signal or an output signal. The takeoff point for the block diagram given as dotted lines in the figure below. Okay, so these are basically the takeoff points. So we have to understand the concept of summing point and takeoff point before reducing any block diagram reduction. Okay, so now we will come to some problems to find that how we will obtain the overall transfer function of this system. So the block diagram of the system is given to us. We have to find out the closed loop transfer function. Either we will call it as closed loop transfer function, we can also call it as basically overall transfer function, overall transfer function, both are same thing. Okay, so now we will see this, how we will solve this. So this is the block diagram. Okay, so this is one takeoff point here, one takeoff point here, one takeoff point here. This is summing point, summing point, summing point. Okay, so let us start the problem. First of all, we will eliminate this particular loop. You can see signals are coming at this summing point and both are in same direction. So this is basically both blocks are in parallel. Okay, so in this case we will simply add it up with sign. So G3S minus G2S. Okay, so if we'll, when we'll eliminate it, we will get G3S minus G2S. Okay, another thing, okay, another thing what we are doing, so we have eliminated this block, so we are having this and this. Now what we are doing, we are shifting this summing point from here to here. So when, so here signal is moving in this direction, so we are shifting summing point from before a block to after a block. Okay, in this signal traversal direction. So what happened, once when we will do this, this block and this block will be in cascade, and this is your feedback, its value is 1. So what happened, whenever we will do this, the associated feedback element will be multiplied with the transmittance of the block or the transfer function of the block by which we are moving it. Okay, so it means it will become H2S. So in the next step, we can see this. Now these two blocks are in cascade. So we have we are having blocks in series, or you can say in cascade. Once you will transfer this block from here to here, so you can see H1S and H2S are in cascade. This summing point will now come over here. So we can draw this, redrawn this like in this manner. So now these two are summing points. Okay, so can we separate these two summing points? First, what we will do, these two blocks are in cascade, these two blocks are in cascade. So in simple, we will multiply them. So we are having block values this and this. Okay, now what we will do, we will separate out these two summing points. If we will move from here to here like this, you can see minus sign come over here and minus sign come over here. So it will become positive. Okay, and if you will come from here to it, plus and minus. So overall sign will become minus. So what we will do, we will write this summing point like this. We will combine these two summing points in this manner. Okay, because we don't want to change, because we want to make a single summing point for connecting this. So we have to take this minus sign. So for making this positive, we are moving this minus sign to this block transfer function. Okay, so you can say H2S minus H2S or H2S into minus 1, the same thing is there. So now you can see, if you will solve it, one portion is this, another portion is this. You can see here one is coming and also this is coming to here. Okay, so these two are in parallel, so it will become, add it up. So when we will add it up, so 1 minus of H2S, this will become 1 plus H2S. And you can see here, this is the forward path and this is basically the feedback path. Okay, so basically you can see this is the forward path and this is the feedback path. So we will eliminate it. Okay, the feedback is basically the negative feedback. Okay, so this will become G upon 1 plus G into H. So whenever you will do this and solve it, you will get this value. Then you can simply multiply by 1 plus H2S to find out the overall transfer function. So you can see this is 1 plus H2S times G1S, G3S minus G2S upon 1 plus G1S, H1S, H2S, G3S minus G1S, H1S, H2S, G2S. So this is how we can obtain the overall transfer function for a complicated system. Let us see another problem. For the block diagram system shown in figure, determine the transfer function using block diagonalization technique when the input Rs at any instant of time is applied to any one station. So here we are assuming that this is the input Rs, this is the input Rs. And what happened here? The input Rs is not applied simultaneously to both these stations, but first it will applied over here and then it will be applied over here. So in such a situation, what we will do, we will assume this Rs equals to 0 here when Rs is applied over here. Okay. So why we are using this summing point here? We are using this summing point here because we want to add this signal with this signal. But when this signal is 0, so there is no need of this summing point when the input is applied at station 1. Okay. So input Rs is applied to station 1 only. So when this is the situation, you can see the changes in the block diagram here. Okay. You can see the changes in the block diagram here. This summing point is basically eliminated because it is not required now. Okay. Another things are same. Okay. Now what we will do basically for solving this, okay, actually this is summing point, this is takeoff point. So sometimes whenever this type of situation arises, then we always don't want to interchange between summing point and takeoff point because it will become very complex process. Okay. So what we will do basically here in this case, what we did basically, we shifted this takeoff point from here to here. So when we will do, we are moving this takeoff point after a block. So this feedback part transfer function will be divided by the transfer function of this block. So it will become H3 upon G3. Okay. Or you can say H3 into 1 by G3. Okay. So this is the amendment. So now you can see, now we are having simple, now the process is simple. Now we can eliminate this feedback loop. G3S is the forward path and H2S is the feedback path. We can eliminate this loop. When you will eliminate it, it will become G3S upon 1 plus G3S into H2S. So you will, and this block is in cascade with it. So you can multiply by G2S. So this is how we have solved it. Okay. So you can see this is how we have solved it. Okay. Now you can see at this particular summing point, when we will eliminate it, this is the forward path and this is basically the feedback path. Okay. So if let us suppose this is A and this is B and the feedback is negative, so it is will become, overall transfer function will become A upon 1 plus AB. A upon 1 plus AB. Okay. So A upon 1 plus AB, when you will do, it will become this value. Okay. So now this overall block will be replaced by this value. So you can see these two are in cascade. These two are in cascade and this H1S is again in the feedback. So what we will do? You will simply multiply because these are in cascade and H1S is in the as the feedback path. So you can easily solve it. Okay. So this is the change. You can see the change here. G1S is multiplied now and H1S is the feedback with negative feedback. So what happened? This will become, if it is A and it is B, so negative feedback will become A upon 1 plus AB. GS upon 1 plus GS into HS. Okay. So this, when we will apply, we are having the transfer function value like this. G1S into G2S into G3S upon 1 plus G3S H2S G2S H3S G1S G2S G3S H1S. Okay. So this is how we have obtained, because when RS is applied, in this case we have assumed that input is RS but output will become C1S. Okay. So this is, we have solved for station 1. When the input is at station 1. Now we will applied input applied at station 2. It means this summing point will now required. So we are applying input over here. We are getting output from here. Let us suppose this time output will become C2S. Okay, and there is no input here. So when there is no input here, you can see what is the role of this summing point to add this input. When this input will become 0, then there is no need of this summing point. But what happened? This negative sign need to be considered. So where we can consider it? We can either consider it over here or we can consider it over here. Okay, so it is up to you that where you will consider this summing point. Okay, so here, so we have eliminated it, and that minus point comes over here. Okay, so this is the block diagram for the station 2 when the input RS is applied at the station 2 only. Okay, so now how we will solve it? So what we are doing basically, we are moving this summing point from here to here. We are moving this summing point from here to here. So what happened? Because signal traversal direction is this, so we are shifting the summing point after to before a block. Okay, so in this case, this transmittance will be divided by the block transfer function. So it will become H2S upon G2S, or you can write H2S into 1 by G2S. Okay, and this you can see here G1S and minus H1S are in cascade, which are coming over here. Okay, so now you can see these two are in cascade. Now here it is important to note that this is the input and this is the output. So you can say the portion from here to here is the forward path, and you can say all other remaining things from here to here, the complete system will act as feedback system, Okay, now we will solve it. So okay, now there is a rule in block diagram reduction technique. Then if there are two summing points which are adjacent to each other and there is no block in between them, so we can interchange those summing points. So what we are doing basically, we are moving this summing point here and this here. So how we will get benefit from it? This we can separate the loops. So after doing this, this will be the situation. Okay, now you can see this is the forward path and this is the basically the feedback path. So you can solve it. It is G2 upon 1 plus G2 into H3. Okay, so we have solved this, and also this H2S by G2S we can solve. Okay, so we have separated this. G2S upon 1 plus G2 as H3, and this summing point will be, this loop will be eliminated. Okay, and then finally this loop will be eliminated. Okay, so this is basically we have written directly how it is eliminated. You can see at this particular summing point what happened. You will see simply this portion. You can see this is the summing point, and at this summing point this and this both signals are coming in the same direction. Okay, so you can see this block and this block both are in parallel. So when both two blocks are in parallel, you can simply add it up with sign. So one sign coming for minus G1S H1S and minus H2S by G2S. So we have eliminated it. Okay, and this loop has also been eliminated, and this is the input. So now what happened here? This is the situation. This is the input. You are getting the output from here, and this whole is the feedback portion. This whole is the feedback portion. So this you can see is in the cascade. This comes first and this comes first, or in series. So you will simply multiply this with this block transfer function with this block transfer function, and the whole come as a feedback. So let us suppose this is A, this is B. Okay, so you can see it will become cascade. In cascade it will become AB. Okay, input is applied from here and feedback is positive. Okay, so simply it will become C2S by RS will become G3S upon 1 plus 1 minus sign will be there as positive feedback is there. I am not considering the signs coming from here. So 1 minus G3A B. So this comes out to be C2S by RS will become minus G2S times G1S, G2S, H1S plus H2S upon 1 plus G2S, H3S into G2S. Okay. So, sorry, this is just the thus we have solved this loop, and the final answer comes out to be this. This is the complete answer. This is not the complete answer. This is basically you can say simply the intermediate portion which we have obtained. Okay. Okay, so this is the overall transfer function which we have calculated after solving this G upon 1 minus Gx, because positive feedback is there. So this is G, and this is basically the 1 minus, if it is H, so this is G into H. Like this you can solve it. Okay. So these are the references. Thank you. Thank you so much.